evening and welcome to TR Physics, and today I'm going to talk about energy levels. Now, energy level diagrams are a first year physics or on the AS course. However, there are elements of the second year physics, namely electric fields, that can actually help. So I'll be predominantly looking at the first year with you're using energy diagrams, etc. But I will bring in a little bit of second year physics, but I will identify when I'm doing that. Now this here is an energy level diagram, and as you can see, we start at the bottom at ground state, and we have these numbers of n equals 1, n equals 2, and it all goes up to infinity. And then on the other side, you have these numbers that start quite big at the bottom, minus 13.8 mega electron volts, and they get smaller the higher you get up the energy state, so the energy levels get 1, 2, 3. Now, basically, the premise of an energy level diagram is something that's unique to different elements. This number here, this minus 13.8 mega electron volts, is the amount of potential that I need to rip an electron out from if it was here. So if an electron was orbiting a proton or a nucleus of an atom and it was at the ground state, this is how much energy I would need to put in to remove it fully from the atom, to ionize the atom. So if this electron was here, if I wanted to remove it completely from this atom, that is how much energy I would need to make it leave the atom. That's why it's a negative number. This negative number implies I have to put energy in to remove it. Now, sometimes when you try to ionize an electron, you don't quite give it enough energy to ionize. But you might give it enough energy to go to another energy level. And up here, maybe we're going to give our element here enough energy to go from here all the way up to n equals 1. Now to do that, I would have supplied this with the difference between these two energy levels. So I would have supplied it with 8.6 mega electron volts. So to go from here to here, that's how much energy I would have had to supply it. It's still orbiting the atom, but that's how much energy I supplied. Now, one of the interesting things about orbits is that unless you give enough energy to help it carry on in that orbit, it will then fall back down, much like this. I'm going to give it some energy to try and leave this gravitational field. It goes up and then it will come back down again because I haven't supplied with it enough velocity to orbit where it is. So it's unstable, so it comes back down to its original position. And that's what's going to happen here. This electron cannot stay in this orbit here. And I've drawn a diagram here. This is the nucleus of the atom, and this here is the orbit where I require 13.8 mega electron volts worth of energy to remove an electron from. I'm going to give it 8.6 mega electron volts. And it's going to move to this orbit, but it can't stay there. It will then come back down again to the ground state. But where does the energy go? This energy will be released as a photon. That would have this much energy. Would have 8.6 mega electron volts worth of energy. You can use the photon energy formula to then calculate the wavelength, the frequency. Now, on these kinds of diagrams, sometimes you are asked on how many different photons could be released. Well, we could go from here to here, and it will come back down, that's 1. I could go from here to n equals 2, and back down again. That's 2. That's 3. But I might have electrons orbiting here. That's 4. That's 5. And that there is 6. So there are 6 different combinations of photons that could be emitted from this element. Now this is important, that these values of these stable orbits are very dependent on different elements. Different elements have their own unique levels, their unique ground states. Some elements it's very easy to rip off the electrons, some elements it is not. And therefore these things reflect. But every single element, because these are unique, will emit their unique pattern of photons, I do apologise. And this will lead us to atomic line spectra in the next video.